All right, getting into correlation and regression, well, specifically correlation in this video, Math 5130, Doug Darbro, let's do it. Key concept, we're looking at a linear correlation coefficient, R, and it's a number that measures how well paired data, quantitative data, fit a straight line. So our data are paired, x comma y. You might think of examining the relationship between someone's BMI level, again the quantitative component, and their HDL, whatever. It just needs to be quantitative. In this case, x will always be our independent variable, and y will be, that should not be, y is out dependent variable. It should be y is our dependent variable. And appropriate for straight line relationships only. So we need to eyeball our relationship and make sure that it is linear. So interpreting scatter plots, when I eyeball this one, I can kind of visualize a line going right up the center of that, indicating that I have a linear relationship. This would have a positive correlation because the trend of the data as x gets bigger, our y values typically kind of tend to get larger. So when I'm down here at, say, an x value of 1, my y values are in the 5 to 10 range, right? But when I get out here to 9, my y values are up in the 20, 25, 30 range. That is the characteristic of a positive relationship. And it's linear because, again, just as I eyeball it, I think most of those points would fall pretty close to a straight line. This is a negative correlation. Same argument. For x around 1, most of my y values are somewhere around 0 to -10. But as I get down here to 9, you can see that most of my y values are much lower, down around -30, -40, -50. That's the characteristic of a negative correlation or a negative straight line pattern. This is no correlation. I don't see any relationship there, no pattern. I don't see a linear pattern at all. So we would say that there is no correlation between x and y because it doesn't follow a linear pattern. And these correlation coefficients have been calculated, and just gives you an idea of where they stand. Any R value close to 0 indicates no correlation. And even though you could calculate the correlation coefficient for this, it would be meaningless because the pattern, I mean, there's a pattern there. It's like an upside down quadratic equation, but it's clearly not linear. No one's ever going to convince me that I can draw a straight line that models this data effectively. So we measured this linear correlation with something called R. It's called a Pearson product moment correlation coefficient in honor of one of the great statisticians, Carl Pearson. And a few properties of this, the R value will always be between -1 and +1. Negative R indicates a negative relationship. Positive R's indicate a positive relationship. One of the first things you have to get through your mind on this is a correlation of -0.8 and a correlation of +0.8 have the same magnitude, the same strength. The negative just indicates the pattern, the direction of the relationship. A -0.8 would indicate that the as I move from left to right, the values decrease. A positive relationship, +0.8, would say as I move from left to right on my x, the y values actually increase. So that's the only difference. And again, it's completely meaningless if we have a relationship that is not linear. And R is very sensitive to outliers, as we'll see a little bit later. So finding R with R, sorry. So I've got some data here, white blood count and red blood count, and these things are paired. So you could think about this as our X comma Y and X comma Y. So we have a pair, about 10 of these, I believe. And if I use R to create a scatter plot, which I'll demonstrate, it's very easy to do. I can see that I have a linear trend. Straight line fits this. Yeah, okay. So I would feel comfortable thinking of this as linear. And I clearly have a positive trend telling me that people with higher white blood counts typically have higher red blood counts. Now, yeah, there's some caveats there, but there always will be. Next thing, putting it at R is really easy. I just typed in the data, called it red, white, did what's called a core dot test for white and red, and I create this Pearson's product moment correlation. We get the test statistic, the p-value, we get the 95% confidence interval, and we get the correlation coefficient, which would be 0.899. I can get the scatter plot by just running plot white-red. So let's interpret this in the context of the null and alternative hypotheses, as we must. That p-value out here, which is statistically significant at the 0.001 level, has no meaning unless we know context. The context here is that the population correlation coefficient is equal to 0. That's the statement in the null hypothesis. The alternative hypothesis is that the population correlation coefficient is not equal to 0. This tells me there's not a linear pattern, linear relationship. The alternative says there is a linear relationship and the slope is not 0. So we clearly, the p-value is less than 0.05, so we reject the null and we conclude that the population correlation coefficient is not equal to 0. Well, what is it? Well, with a 0.95 probability, we can say that it's somewhere between 0.62 and 0.98. So this Greek letter, this is called rho. So rho is the population correlation coefficient, and it's estimated by the correlation coefficient of the sample, which in this case is 0.8998554. Finding R with StatCrunch, you don't get as many bells and whistles with StatCrunch for the correlation coefficient, but you get information. So enter the data in, go to Summary Stats, go to Correlation, select your columns, red and white, select a two-sided p-value, and hit Compute. And when you hit Compute, you'll get this output right here. So it gives you the correlation coefficient for the sample estimate, same thing we got before, and in parentheses it will give you the p-value. It doesn't give you the test statistic, which in my opinion is not good. And there may be a way to get that on StatCrunch, but I haven't figured it out yet. Again, I'm not a huge StatCrunch fan, as you know. So the formula is quite messy. So we will always use technology to find our correlation coefficient for the sample. Now, spurious correlation. A spurious correlation is a correlation that actually calculates out to have a really high R value, but it just doesn't mean anything in terms of having an actual association. If we look at the relationship, I'm from Kentucky, so I'll pick on Kentucky a little bit. If you look at one variable, people who drowned after falling out of a fishing boat, actually highly correlates with the marriage rate in Kentucky. In fact, it's crazy, but the correlation is 0.95, which is extremely high correlation. But come on, we have to inject a little bit of common sense, if you will, and say even though the correlation coefficient is extremely high, this falls under spurious correlation because the two just aren't related. So just because you put two variables into a technology, a statistical software package, and you hit the right buttons and calculate the correlation coefficient, it doesn't necessarily mean that the correlation has a meaningful interpretation. Another thing, correlation does not imply causation. Don't go there, just don't do it. It just does not. All right? So a couple of common errors involving correlation, assuming correlation implies causality. It doesn't. It just examines the strength of the relationship between two quantitative variables and not eyeballing the relationship beforehand and making sure that it is truly a linear relationship. And again, that's done by an eyeball test in the simple linear regression world. So don't ignore those. All right.